Hello everyone. So guys, in the previous lecture we have learned that how multipath routing is done and what is essential to determine in case of multipath routing. And we have ended with the thing that if we want to do multipath routing, then the main thing that we have to find is the value of lambda ij, and that is the traffic distribution. So now in this lecture we will see that how we have formulated the problem, and which basically deals with the energy balancing and the delay aware, and and after that the solution of that particular formulation gives us the value of lambda ij, and how this this particular lambda ij is playing its role during the in case of during the formulation basically. And now let us start. So guys, as we know that incoming data on a particular node should be transferred completely towards the its parent node. So and the flow condition says the same. Flow condition says that the first equation is representing the flow condition, and what this equation says, gi is representing the generated data, that is the data which is sensed by the ith node. Fine. And the second part of this particular on the left hand side of the first equation is representing that this is the received data, and the received data by the ith node from the k child nodes, or we can say the kth child node basically. So ldk is representing the load value on the kth node, and out of that particular load value, for example this ldk value is the 10, and suppose lambda of ki is value 0.2. Because as we discussed in the previous lecture as well, the value of lambda lies between 0 and 1. So let us assume that value of lambda ki is 0.2. So what this kth node will transfer towards the ith node, it will transfer the 2 unit of its load towards the ith node out of the total 10 units of the load. Fine. And when we do the summation over all the k child nodes, then what it refers that the k child node will completely transfer its data towards the ith child node, or we can say that ith node has received the data from all the child nodes. Yeah, that is much correct. And yes, the right hand side is representing that ith node is transferring its data towards the jth parent node. Fine. So this is the whole equation explanation. And now the energy consumption during receiving of the data in a single round is given using the second equation. And what this equation says, this zeta I is representing the energy consumption of the ith node in receiving the data over a given traffic distribution lambda. And then this the right hand side is representing ldk multiplied by lambda of ki. So what it will give us that the amount of the data that kth node is ith node is receiving from the kth node, and alpha 3 is representing the energy consumption rate in receiving the data. So and the summation over all the kth child nodes of this particular ith node, it will give us the energy consumption in receiving the data by this particular ith node. And similarly, the energy consumption during the transmission in a single round is given using this particular third equation. And what this equation says, this I have discussed in the first equation, that gi plus this part, that is ldk into lambda of ki. So this is basically representing the total load value on the ith node, and when it is multiplied with summation of j belongs to parent of I, lambda ij into cij. So what it says that okay, this is the total load value, this first one, and okay, out of this total load value, this lambda ij, ith node, is transferring the data towards the towards the jth node, and Cij is representing the energy consumption rate in transmitting the data. So what now the total energy consumption we can write like this, that is energy consumption in transmitting plus energy consumption in receiving the data over a given traffic distribution lambda. Fine. So then once the energy consumption is calculated, the network lifetime can be defined as network lifetime with respect to the node I for a given traffic distribution lambda is the ratio of initial energy of the ith node to the total energy consumption of the ith node in a single round. So what it will give us that that is the lifetime of the ith node in terms of rounds, that is for how many rounds this node is going to be alive. And once we have determined this lifetime value, then we have defined the first objective for the energy balanced multipath routing as what this objective says. Okay, what we are trying to achieve is the node which is having the first part of this objective is representing the node which is having minimum lifetime among all the sensor nodes in the network. We will try to maximize that particular value for a given traffic distribution lambda. And what it will result into, it will try to maximize the first node depth, or we can say that it will delay the first node depth as much. We will try to delay the first node depth as much as possible. And the second part of this objective is representing that we are trying to minimize the total energy consumption with respect to all the nodes in the network, because zeta I we have calculated in the previous slide that zeta is representing the total energy consumption. So we will try to minimize the total energy consumption as well. Along with that, we will try to maximize or we can say we will try to delay the first node depth. So these two objectives we have achieved, and it is subjected to the condition that this is summation of lambda ij is equals to 1, that this particular equation we have discussed very well in the previous lecture. And the last equation is representing the flow condition that I have discussed in the previous slide. Well, okay, now if we as we know that in case of multipath routing, the packet needs to be segmented before sending towards the towards the parent node. And after that, all these segments have to be reassembled at the base station. Fine. So this process of segmentation and reassembly creates the delay into the process. And the second parameter that creates delay is because the packets or we can say that the packet segments travels over different path length, so that will also introduces the delay parameter. So all these kind of delays, that is segmentation and reassembly, and due to increased path length corresponding to a single segment of the packet, so all these delay we have tried to minimize these delay in case of our case. And how we have defined is or I can say how we have catered with the problem of delay minimization. Like here, the second objective we have defined, and what this says that the first objective, the first part is the same as the first objective, and the second is the that we will try to minimize the delay value corresponding. This tau I is basically representing the delay value for a given traffic distribution lambda for the ith node. So we will try to minimize the delay value corresponding to the node which is creating maximum delay, and it is subjected to the condition. These conditions are same that I have discussed in the previous slide. And after that, this the tau value, this delay value, we have estimated this value in terms of hop count, and this hop count is determined using this equation, this last equation. And what this says that if ith node is belonging to the base station, then the hop count value will be 0. Okay, fine. What this says that the base station will always have the hop count value 0, and once we move away from the base station, then we will change the hop count value corresponding to this particular first case, basically, of finding the hop count. Fine. And yes, now these objective 1 and objective 2 are the sequential quadratic programming, and so we have tried to solve these sequential quadratic programming using a mathematical tool which is named as fminimax in MATLAB. And guys, these mathematical tools requires very large amount of memory, and also that they creates delay in their processing, and also the time the complex and we can see that the time complexity is very high. So to minimize those things, that is to minimize the requirement of these mathematical solver, we have solved these quadratic programming problems using we have tried to solve these quadratic programming problems using particle swarm optimization. And the solution that we have obtained, that how we will try to obtain the solution of these quadratic programming problem using particle swarm optimization, we will discuss that particular part in the next lecture. And here we are ending this particular lecture here only. Yeah, thank you.